Hi guys, this video is to introduce how to calculate pH value for weak acid and a weak base. Okay, now as usual, I'll show you the derivations of the formula before we go into the questions posted in OL, right? So first, how to calculate the pH for a strong acid. Now, see, to calculate pH for strong acid, I believe everybody's still remember how to do that. So HCl dissociate in water. I'm sorry, it's supposed to be a complete reactions. My bad. HCl is a strong acid, right? So it's supposed to be completely dissociates into H plus and Cl minus. Now let's say the initial concentration is 0.5 mole per dm cube. So I'll expect the concentration of the H plus here equivalent to 0.5 mole per dm cube. Right? That's what we call strong acid, a fully dissociate. So what happened to the pH value of this acid? So we calculate pH equals to negative log concentration of H plus equals to 0.5, right? Just sub in the value. So minus log 0.5. You will get a pH value of 0.3. Done. Right? So this is for strong acid, straightforward. Now, what if I have a strong base? This is just a revision, guys. What if I have a strong base, let's say, for example, NaOH, and it dissociate in water to get Na plus and OH minus, 100% dissociations. So if I have 0.5 mole per dm cube here, I'll be getting 0.5 mole per dm cube here. Okay, so what is the pH? We can't calculate pH straight away, so we need to calculate pOH because we have the concentration of OH. So minus log concentration of OH minus, which is equivalent to log 0.5. Then you will get 0.3 here. Okay, pOH equals to 0.3. And then that's not the final answer. What is your pH? pH plus pOH equals to 14, and that's how we get the pH scale under room temperature. All right, but if the temperature change, the scale will change. Okay, if you still remember why, right? So we learned that in Sem 1. Ask me again if you need help on that. So this is the formula. So what we're going to do, pH equals to 14 minus 0.3 then, if you want to get a pH. So the pH of this strong base is 13.5. Makes sense. Like pH more than 7, 13.5 is a base. So that's how we calculate strong acid and strong base if it is 100% or fully dissociates. Now what if we talk about weak acid and weak base? Let's talk about weak acid. So let's say I have ethanoic acid, again, CH3COH. It partially dissociates into CH3COO negative plus H plus. Now this is a weak acid. Meaning what? Meaning that it partially dissociates. If I have 0.5 mole per dm cube here, I will expect the concentration of H plus produced is definitely less than 0.5. But this is just an estimation. Now, how do we know the exact value or the actual concentration of H plus produced from this ethanoic acid? We need one thing, Ka value. We need a constant. And Ka, we call it as acid dissociation constant. Okay, and this constant, no worry, is given in a data booklet for most of the weak acid. Okay, for most of the weak acid. And a reminder for you, only weak acid with a Ka value. Okay, only weak acid with a Ka value. So if it is a strong acid, you don't expect to see any Ka value because it fully dissociates. When something partially dissociates, you need a constant value to measure the extent of dissociation, how much they actually dissociate. So we need a constant value to do some calculations. So we'd have a Ka values. Make sense? Okay, let's see. We are going to calculate the pH values for these weak acid. Now, how are we going to do that? First, we need the Ka value of this acid. So I just made up a value here, guys, for ethanoic acid, Ka values, because you just need to know the calculations, right? So I just made it up. Ka value for ethanoic acid is actually equals to 1.7 times 10 to the power of negative 4. Okay, that's Ka value for ethanoic acid. And I have the initial concentration of the acid. So how are we going to do? Ka equals to concentration of the product, COO negative, concentration of H plus over concentration of the acid. So I'm writing the expressions, product over reactants. This is your Ka. Okay, and then can I say that concentration of H plus is always equals to the concentration of COO negative? You see that? Can I say the concentration of this same as this? It's 1 to 1, right? The ratio is always 1 to 1. If I have 0.5 of H plus, I should have 0.5 of CH3COO minus. That's the ratio. So I can say that, yes. So Ka value in turn become, I can twist it, H plus square over concentration of the original acid, like that. Since both are the same, I can turn this into H plus, therefore I get H plus square. All right, and then I can just move around the equations. I can get concentration of H plus equals to square root of Ka multiplied with concentration of the original acid. So this is actually the formula for you to calculate the concentration of H plus ions for a weak acid, the actual value. Not like this, less than 0.5. Of course I know it's less than 0.5 because it's partially dissociated, but what is the exact value? Using this formula. All right, so just need to remember this formula, then you can get the H plus. And what happened next once we got the H plus? Then we just use pH equals to negative log H plus. We use the same formula like we calculate strong acid. This is a must, and then automatically you will get your pH value. That's it. So just need to do one extra step for a weak acid, which is this. Okay, which is this formula before we come into this final equations to get the pH value. So that is for weak acid. Now what if we have weak base? All right, examples of weak base. Let's say I have ammonia. All right, it dissolves in water, sorry. It partially dissociates into ammonium and hydroxide. So what if the concentration here is the same, 0.5 mole per dm cube? So what do you expect here? The concentration of OH minus less than 0.5 mole per dm cube because it's a weak base. Again, because it's partially dissociated, we need a constant Kb. This is base dissociation constant. B stands for base. And of course, it have its own value. So Kb for ammonia, let's say I made up the value 1.07 times 10 to the power negative 4, let's say for example. Okay, that's a Kb. And what would be the expressions for Kb? Kb equals to the product over reactants, concentration of ammonium plus OH minus divided by ammonia. And you may asking these questions now, why don't I include H2O in the expressions? H2O is a water, and that's why all this are getting its concentration, because concentration is something per unit volume of water. So water has no concentration, which is a constant. So we don't put it in. So this is the expressions for Kb. Even though you have water in it, we ignore it because it's always constant. And what to do? Can I say concentration of ammonium always same as the concentration of hydroxide? Can I say that? Yes, definitely, because it's 1 to 1 ratio again. So I can rearrange them. I can put Kb equals to concentration of OH minus square over concentration of the original ammonia. And then rearrange them again. I get concentration of OH minus equals to square root of Kb multiplied with concentration of ammonia. So that is another equations you need to know when you're calculating the pH for a weak base. All right, and what is the next step once you've got the concentration of OH minus? Then we calculate POH equals to a value, and then 14 minus POH equals to pH. You have to do these 2 steps. So for weak base, you need 3 steps. First, you get the OH, the exact value. Second, you calculate the pOH. Third, you calculate the pH. Make sense? So yeah, that's how you do. That's how you calculate the concentration for a weak acid and a weak base. All right. So I'm going to show you the example posted in OL in terms of its solution. So I erase that. Let's move on to this. Now these are the questions posted. Okay. Let's do it together. First, calculate the pH value for 0.1 ethanoic acid. Ka is given. Obviously, this is a weak acid when Ka value is there. All right. Then what is the formula, guys? Concentration of H plus equals to square root Ka multiplied with concentration of the acid, the ethanoic acid in this case. So we just put in the value. Ka value is 1.7 times 10 to the power negative 5. All right. Multiplied with, what is the original concentration? 0.1. And then you square root the whole thing. All right. Square root the whole thing. Then you will get the concentration of H plus. Let's do the calculation here. 1.7 times 10 to the power negative 5 multiplied with 0.1, and then you square root your answer. There you go. You get 1.3 times 10 to the power negative 3. Now that's your H plus. So what is your pH value? pH equals to negative log 1.3 times 10 to the power negative 3. You will get your pH value. So minus log answer, I get 2.88. Now that's your final answer. Okay, so you have extra 1-2 steps before you get a final pH value compared to a strong acid. So this is for strong acid, and let's move on to strong base. All right, strong base, again, I have, let me change the color. pH value. Calculate the pH value of 0.2 molar of ammonia. Kb is given. So what is the formula? Sorry. Concentration of OH minus equals the square root of Kb multiplied with concentration of the original base. So sub in the value, 1.8 times 10 to the power negative 5. Multiplied with ammonia, which is 0.2, the original concentration. And then you square root the whole thing, you will get the OH minus. So what's your OH minus here? Let's do the calculations. 1.8 times 10 to the power negative 5. All right, multiply with 0.2. And then square root the answer. You will get concentration of OH is equivalent to 1.89 times 10 to the power of negative 3. Okay, that's the concentration mole per dm cube. So you see that, guys? Let me explain a little bit here. I'm using a 0.2 mole per dm cube of ammonia. All right, it's a weak base. So what is the concentration of OH minus produced from this 0.2? Only 1.89 times 10 to the power negative 3. It's just a small portions from 0.2, isn't it right? So that proven that it's proven that ammonia is partially dissociates in water from 0.2 total concentration. Only 1.89 times 10 to the power negative 3 mole per dm cube of OH produced. Okay, so this is not the end. We want the pH. So first we calculate pOH since we got the OH concentration equals to minus log 1.89 times 10 to the power negative 3. So that's how we calculate pOH. So minus log answer, I get 2.72. All right, and then pH equals to 14 minus pOH, 2.72. So you get 11.3, about that. Okay, 11.3 pH value. So it makes sense, guys. It's a base, a weak base. So the pH is about 11.3. If you get 14 or 13, that is a bit impossible. But I mean, it's in a way it works, but it depends on the concentration. But the concentration is just 0.2. Right, so 11.3 is the pH for the weak base, and ethanoic acid is 2.88. You see that? Now, before we end the video, I'm sure some of you have these questions. Now, 11.3, all right, it makes sense. But what about this ethanoic acid? It's a weak acid, but the pH value seems quite low, 2.88, right? I thought pH 2 or pH 3 is actually meant for strong acid. No, that's the point. So you're wrong if you think that anything showing you pH 2 and 3 is a strong acid. No. Now, when we say strong acid or weak acid, it's all about what? It's all about the dissociations of an acid. How much they dissociate. If I have 0.1, it dissociates into 0.1 of H+. That is fully dissociate. But the pH can be high. The pH can be pH 4, pH 5. It doesn't matter whether you get a low pH or a high pH. It's a matter of the dissociations. So we can't say that I have a low pH solution, so this must be a strong acid. No. You can have a low pH solution, but that can be a weak acid because it partially dissociates. Let's say I have 10 mole per dm cube of ethanoic acid. 10 mole per dm cube. It's highly concentrated, right? Even though it partially dissociates in water, the amount of H+ produced will be quite big, right? Because the original is 10 mole. Even though it partially dissociates, the concentration of H+ can be quite high. And then you use that to calculate the pH will appear to be very low. Okay, the pH can be 1 or 2 or even 0.3. But does that mean this is a strong acid? No. Okay, as long as it partially dissociates, then we call that as a weak acid. It's not a strong acid. So it's a wrong concept to think that when I have a low pH solution, it is always a strong acid. When I have a high pH solution, it is a weak acid or even is a base. No, it all depends on the dissociation. All right, so I guess that's it for the calculation. Thank you.